Good morning, everybody, and congratulations to all the award winners. I'm happy to introduce Dr. Atul Sharma today. Dr. Atul Sharma is a professor in the Department of Mechanical Engineering, IIT Bombay. His contributions are on development of a range of novel and efficient computational tools and its application to a large number of time-consuming simulations and analysis of this resulting big data for a wide variety of problems in CFD. He also demonstrated simulations for challenging industrial problems such as circuit breakers, power transformer, and printed circuit heat exchangers. Most of his advanced CFD research contributions are computational two-phase flow and computational fluid structure interactions. He is providing training program in various colleges and industries by starting a YouTube channel called CFD Made Easy and publishing a textbook. His contribution in the textbook is to make CFD easy enough to be taught at the early undergraduate, so that can enable his vision of make CFD solver in India. He has supervised more than 16 PhD theses. Professor Sharma is a fellow of INAE. He has published 88 articles in 35 different reputed journals, including a Journal of Fluid Mechanics, Physics of Fluid, and Langmuir, etc. Presently, he is an associate editor of Sadhana. He has received Departmental Award for Excellence in Teaching during 2019. With this, I welcome Professor Sharma for his talk on discrete math-based computational fluid dynamics. Professor Sharma.
I welcome all of you to this Institute Award Lecture Series, where the title of my talk is Physical Law instead of Partial Differential Equation and Discrete Independent of Continuous Math-based Computational Fluid Dynamics. I would first of all like to thank IRCC for giving us an opportunity to present our work and the jury considering our book that is published in Computational Fluid Dynamics and a review article for the dissemination of research award. This award is primarily for the book that was published originally international edition by Wiley and paperback low priced edition by AnyBooks New Delhi. And recently this book is has come up with a version. It's already online in the Springer. I'll start with the motivation of writing this textbook. As a student, I had always been motivated with Professor S.V. Patankar, who is considered as a father figure in this area of CFD. He has written a textbook in CFD, which is worldwide the most popular book in the world. And I'm proud to mention that he is an alumni of IIT Bombay. He did his MTech from Department of Mechanical Engineering, IIT Bombay. And later on, he did his PhD in Imperial College London, and then he was a faculty in University of Minnesota. I have dedicated my book to Professor S.V. Patankar. With this background, I want to mention that in our previous generations, there are a lot of Indians who have contributed enormously to the subject of computational fluid dynamics. But most of them have contributed in the Western world. And in today's context, when we talk of make in India, it's very relevant that this application software, which is also like an app, the apps that we are making, this physics-based simulation software, we are not making in India. There have been some developments which we are proud of in India, but as far as you see the commercial software, we do not have any commercial software from India. So this has always motivated me that in this present generation, it is our responsibility to train the students as well as researcher in this area. So my motivation has always been into how to make the CFD easy enough to be taught in an early undergraduate curriculum, because if we teach them early in the undergraduate curriculum, this is subjects which involves developing computational skills and mathematical skills. So if we can teach them right now, the subject is in close to the final year, and that too like an elective. So the students, if they are exposed to this subject, which is a skill development course later in the final year, then they do not have opportunity to do a project or they can think of startup. So my biggest motivation has been how to make this subject easy enough so that it is taught in as early as 4th or 5th semester. Well, I had not only restricted my teaching to IIT Bombay, I had been teaching through CDEEP to outside and going to various colleges all over India to take lectures on CFD, where I have realized that most of the students and even teachers, and as you know, most of them are in the private colleges in our country, they feel that this subject is too mathematical, and that's why this is considered to be an advanced subject and it is put at the in the final year course. So this has always motivated me to fulfill my vision of introducing it in early undergraduate curriculum. It should be more of a physics and less of a maths. So in this regard, I had come up with a physical law and discrete math-based algebraic formulations for CFD. I have also come up with an insightful and intuitive approach to CFD, where I have come up with a virtual video camera-based intuitive perspective to CFD. I've also come up with a comprehensive development application analysis based comprehensive perspective of CFD that has been presented in this book. So let me first start with physical law and discrete math based algebraic formulation for computational fluid dynamics. In fluid dynamics and heat transfer, we commonly start with a conservation law, mass, momentum, and energy conservation law. We apply to a control volume, and while applying to a control volume, I have highlighted in my book that there are two types of transport term that we encounter. First, which is called as a flux term, and the second, which is called as the volumetric term. Then in an undergraduate course in fluid mechanics and heat transfer, we derive differential equation by applying the conservation law to a control volume and then applying the limit delta x delta y tends to 0 or delta volume tends to 0. So when you have a flux term, the total quantity is expressed in terms of flux multiplied by surface area. So when you divide by volume, surface area divided by volume give you the length scale in the denominator, and then you end up with a derivative, spatial derivative of the flux term. And we derive the governing partial differential equation, which we call as the continuity, momentum, and energy equation. And if you see all the books in CFD, this subject is around 50 years old, and till now all the books in CFD, they start with for the governing equations for CFD is an algebraic set of algebraic equations, and what they do is that they start with these differential equations. So if you see all the books in CFD, they start with differential equations, and then to develop the algebraic formulations for computational fluid dynamics, they do volume integral, apply Gauss divergence theorem, then they apply certain mathematical approximation. So this is so when a book starts with a differential equation, obviously most of the undergraduate students feel that it's too mathematical. So this has been the barrier, and this has motivated me to come up with more of physics, less of maths, and to derive the governing system of linear algebraic equation, which is an algebraic formulation for discrete flow properties. So this conservation law is like a mother, and this differential equation is like a child born using the continuous math. So I had come up with a strategy where I say that instead of using the partial differential equation presented in my book, we're starting with a physical law, which we always start in our undergraduate course in fluid mechanics and heat transfer, and using a discrete math but independent of continuous math based finite volume method. So I have found out with the formulations, come up with the formulation and presented in the book to derive the same set of linear algebraic equations which are governing equations in CFD using the physical law and discrete math based finite volume method. I have come up with this approach while teaching CFD through distance educations and IIT Bombay. Somewhere around 2007, 2008, exactly I don't remember because I had been trying hard to work to make this subject easy enough. However, when and in 2013, I had taken 1 year sabbatical leave when I started writing the book. So I was unaware that somebody somewhere in other part of the world has similar ideas. But when I wrote the first draft of my book and I got the feedback from the reviewer where they pointed out to this paper, and I was pleasantly surprised to see the paper that is published in Journal of Computational Physics in 2013. Title itself says why starting from differential equations for computational physics, and this is something which I have come up with to make this subject of physics less of maths. Okay, this is I would say the starting point of the physical law based finite volume method. So in the abstract of this paper, he has mentioned, Professor Tutti has mentioned, we can get an algebraic formulation avoiding any arbitrary process of discretization of differential equations. So he has pointed out that starting with the differential equation, the process that we are doing is like an arbitrary process. And he has mentioned that if we can avoid this differential equation and if we have come up with a formula, it has a great merit of maintaining close contact between the mathematical description and physical phenomena. Professor Tonti has further mentioned that the exact solution that is promised by the differential equation is hardly ever attained in practice. By contrast, the great technological advancement of our days is made possible by the fact of being able to have an approximate solution, in particular a numerical solution to the problem posed by the technique. So this exact solution where we obtain velocities, pressures and temperature as a function of spatial and temporal coordinate. This exact solution is like an infinite resolution video camera where you can substitute any value of x, y and time and you get a solution. But as all of you know that for a general fluid mechanics problem, it is not possible to get an exact solution. So for almost all the real world problem, what we have is like an approximate solution, which is like a finite resolution video camera that is through CFD. I found another paper by Desmond et al. In 2005, where he has mentioned since the advent of computer, there is an enormous development in the discrete mathematics. However, if we ever change our habits of considering the differential continuous formulation as indispensable and one work on discrete independent of continuous mathematics, it will lead to an increase as well as enrichment in the range of application. I would like to particularly highlight that he has pointed out to change our habits. Probably we have been addicted with a habit that there is no, the computer and the discrete math came much later than the differential calculus. So probably we have been addicted with differential calculus for generations. So when CFD came and the formulation that was presented, it carried on the habits of using the differential equation for the algebraic formulations. So in my book, I had presented that discrete independent of continuous math-based approach will lead to much better physical understanding as well as development of better simulation methodology in the various branches of science and engineering. Now I'll highlight the key difference between the analytical and the computational approach that is followed in fluid dynamics. So key difference between the analytic, I am presenting here showing you the specific case of a heat conduction, key difference between analytical and computational heat conduction. So in both the cases, when you have analytical versus computational, you take a control volume, but the difference is in analytical approach, you apply the limit delta x, delta y, delta t tends to 0. So you consider the control volume as infinitely small. Whereas in computational course, you take delta x, delta y as finite, but small enough for accurate solution. In a analytical course, you take the spatial and temporal coordinates as continuous. In a computational course, you take it to be a discrete, where it's like a pixelized representation. In both the cases, whether you consider analytical fluid dynamics or a computational fluid dynamics, we start with the physical law, such as for heat conduction, it's the energy conservation law. And when we apply to a control volume, there are two forms of the energy conservation law which we have studied. One which we have studied in thermodynamics course, another which we study in a heat transfer course. Now, if you see the variable that is presented in a thermodynamics course, in a thermodynamics course, the heat is presented on an amount of basis. In thermodynamics, we talk of amount of heat. Whereas in case of a heat transfer course, we talk about the rate of heat transfer. So while presenting this discrete framework, I was struggling hard for close to 3 years because it's easy to start something, but it's very difficult to close the book in a solid foundation. So one day, after 3 years, I was going through the classical book on heat transfer by Incroper and David, where I found that he has presented two different forms of the energy conservation law, but I improvised on those presentation and I came up with a discrete form of the energy conservation law, where the idea which I used is for a computational fluid dynamics, to use a discrete math, we should use a discrete form of energy conservation law. So for the discrete form of the energy conservation law, I came up with an idea that we should use the statement of energy conservation law, what we have found in the thermodynamics course, but that is amount basis. This is the amount of heat transfer which is entering, this is the amount of heat transfer which is leaving. but we should express the variable, which is this small q, on a rate basis. So I have expressed here, you can see the rate of it when you when know is so this is the discrete form conservation law from where we start. And in our undergraduate heat transfer course, we apply this continuous form of the energy conservation law to derive the energy conservation law in heat transfer. Whereas using this discrete form of the energy conservation law, I had shown in the book how to derive the first in terms of the variables and finally in terms of the temperature. So finally, in analytical fluid dynamics, we do infinitesimal control volume based differential formulation, whereas in a computational course we do a finite control volume based algebraic formulation, where we express this. This is the system of algebraic equations that we derive taking a discrete grid points, which are like pixelized representation. The initial condition and boundary condition, which gives us the first picture of the fluid dynamic movie that we generate through CFD. In an analytical course, it is continuous. The boundary conditions are continuous, whereas in a computational course, here they are discrete in nature. And if you see the solution, again, the solution is in a functional form in an analytical course, and it's a discrete form in a computational course. So the analytical solution are like infinite resolution virtual video camera, whereas CFD is like a finite resolution video camera. In both the cases, if you look closely, you generate one set of equations. Just for an example, in an analytical course, if you develop and derive an equation z is equals to x into y. In a computational course also, we express it as one equation, but it is in terms of indicial form, which is suited to recursive computations. Yeah, so I have introduced the definition of the computational fluid dynamics with a different perspective, where I say that in CFD is a subject where you learn to develop a product, which is a CFD software, and then you learn to apply it, and finally you try to come up with a story which is scientifically interesting by doing an analysis. And I have mentioned that if you talk of any movie, there is a actor and there is a character. So the actor in the fluid dynamics movies are the flow properties like velocities, pressures, and temperature, and the characters are like boundary layer, flow separations, vortex formation. Similarly, we have some certain engineering informations. So we try to correlate both of it and try to make up a story. In my book, I have also created a website where I had created certain movies. So this is like if you consider, if you're standing in a river, if you're in the top view, this is like circle and the flow is passing from left to right. This is a fluid dynamics movie where I call this movie, here the actors are like velocities and vorticity, and here the actors are like pressures and the streamline. So when you play this movie, these are like scientifically exciting movie, and this is the variation of the temporal variation of the lift and drag coefficient when you have a periodic flow. So when we correlate this scientifically exciting movie and engineering movie, you can make a story out of the fluid dynamic situations. So this is the book which is basically on three parts. This is like building the foundation for the course, introduction essentials. This is like any product development is component by component development. So this is like a first component, conduction, then advection, then the combination of these two. So this is like a modular development. This is for a Cartesian geometry problem, and this is for more industrial relevant complex geometry problem. So with this, I had come to the end of this talk, and these are some of the feedback which I had got from the book from the Amazon website. And here I would like to acknowledge my MTech supervisor, Professor J. Srinivasan, who introduced me to the fascinating world of research in thermal and fluid science. Professor Vishwaran, who's my PhD advisor, with whom I learned the systematic way of CFD development. Professor Muralidhar, who has been the editor of an edited book which I wrote during my PhD, and he's also written the foreword for my book. I would also like to thank CDEEP, where Professor Kannan Madhugla, when he was the head, he gave me an opportunity to teach through distance education program. Professor Phatak also gave me an opportunity to teach through distance education. Professor Amit Agarwal, who had gone through my book systematically and gave me some really good suggestions for remarkable changes in the book. I would also like to acknowledge the contribution of few of my students during this book writing process. Thank you for your attention.